Sarah, I have a simple request that may be more difficult than you think. All I'd like you to do is to tell me what a chair is.
Well, you sit on it.
Okay, I can sit on a bed. Is a bed a chair?
No.
Okay, a sofa. I can sit on a sofa. Is a sofa a chair?
No, because you can fit more than one person on a sofa.
Okay, so a chair seats only one person?
Yeah.
How about a stool?
Well, it doesn't have a back.
Well, a chair has to have a back?
Yeah.
Okay. How many legs? Is there a three-legged chair?
No.
No. Well, ordinarily you think of a chair as having four legs.
Yeah.
Now you see, I asked you a very simple thing to define a chair, which you've seen hundreds of them, right? And you know a chair when you see it, yet you had difficulty defining it. And the reason I wanted you to define it is because we're sort of going to investigate semantics, the science that studies the meaning of words. And they have found certain sort of rules that I think you ought to know about because you use words all the time.
Yeah.
Here are a bunch of household furnishings. I would like you to separate them into chairs and non-chairs.
Okay.
Then see if we can define a chair properly.
Gee, these are pretty small household furniture. Well, this is definitely not a chair because you could fit two people on there.
Two people on it, okay.
More than one person.
All right.
This is not a chair because you lay on it.
How about that? You can sit on that. That's four legs.
Yeah, but you eat at it.
It's a table, okay. So here are all chairs. Notice, by the way, that scientists have said that words never say all about anything, and they always emphasize the similarities and not the differences. Look at the chairs. See how you're illustrating the chairness of something, yet you have eliminated the fact that these two have arms. You've not talked about the color at all, or the seat, or the fact that a little baby can sit in this one. So just remember, chair, the words never say all about anything, and they always emphasize the similarities. In fact, the only way, right here, to be sure that we both understand what we're talking about is to say, that is a chair, and you point to it.
Oh, okay.
So that means that you're not using words to define words, you're pointing to the thing, and that defines it.
Yeah.
That, by the way, is not a chair, right?
Yeah, it's a footstool.
It's a foot, no. I'll show you a footstool. Here, move those pieces of doll furniture out of the way, and I will show you a real footstool.
Nice footstool.
Isn't it a footstool? It's a stool made out of feet, right? Obviously, the designer of this was using words in a special way called a pun, in which he was using the idea of foot in two different ways. Ordinarily, you think of a footstool as something on which to rest your feet, right?
Yeah.
Right. This one is made of feet. Okay. Now, would you carefully open this box, because inside there's a frog.
Won't the frog jump out?
Well, go ahead, open it. Take the frog out and put it right there. That is a dressmaker's frog. And if you were a dressmaker and we were working together and I said, hand me the frog, you'd know exactly what I was talking about. So
Now I would.
Words have special meanings depending on who says them, because various professions have different words that have special meaning in them. In fact, you probably thought I was going to have something like that, right?
Yeah.
But if you pointed to that and said frog, I would assume that a frog was made out of ceramics. So that's not a frog either, is it?
No, it's just a ceramic.
You see how using words can very often lead to different ideas entirely. And I have one idea as a result of the using of the words, and you have an entirely different idea.
Yeah.
In fact, you can sort of think of words as maps for ideas. And maps never have all the information about a territory, do they?
That's true.
Yeah, okay. Then words can have many meanings. For example, what's the difference between determined and stubborn?
Well, determined is when you're confident that you are going to do this.
Okay, that you're firm.
Do something.
You're firm, right. But isn't that firm too?
Stubborn is when you're unusually firm.
Unusually firm, okay. It has a negative connotation. You know what the word connotation means. So words have all kinds of meanings piled on top of this simple meaning. How about this?
Well, boss sort of gives you the impression that a boss is really bossy.
Bossy could be, right? An employer?
An employer hires employees.
Well, in other words,
And people,
scientists work very hard at using words that have as specific a meaning as possible. And if you notice, if you've ever read any scientific papers, they seem sort of dry because they don't use a lot of colorful words and boring. Well, actually, they're using words as, to mean very specific things, so other scientists who read them know exactly what they're talking about. And they don't use words like bossy or stubborn. Okay. Finally, what is a lozenge?
well, it's something you suck in to make your throat feel better.
For sore throat?
Yeah.
As a matter of fact, a lozenge originally was a nice saying. And when somebody died, they put the saying on a tombstone. So then they put the saying in a diamond shape. So pretty soon, a lozenge was a diamond shape. And in fact, in architecture today, there is a lozenge, a diamond shape, that architects use it all the time. Then a cough drop manufacturer made cough drops in the diamond shape. So pretty soon, they were called lozenge because of their shape. And here is the lozenge, right?
Yeah.
Not diamond shaped anymore at all.
Oh, they're circular.
Yeah, they're circular because now the word lozenge means cough drop, or and while it originally meant a nice saying. So the reason I wanted to bring this up is that it depends on when the word was used. Because well, a refrigerator 20 years ago meant something entirely different than it does today, right? In fact, who's that?
Me. Well,
That's you. This is you several years ago. So they could call this person Sarah a long time ago, right?
but it's not me now.
But it's not you now. Okay.
Okay.
So let's sort of summarize. First of all, words never say all about anything.
Yeah.
That they always emphasize the similarities and forget the differences.
Yeah, and they depend on when they've been said.
When they say them and who says them.
Yeah.
So be very careful. Words have all kinds of strange and wonderful meanings.
Yeah.
Here's a bag that has lead shot in it,
Holy.
and it has potential energy. Do you know what that means?
It means coming together or
No, it means stored. Stored energy. In other words, because of its height above the table. When I let go,
It'll drop down to
right.
the table.
Well, okay, then it went to kinetic energy, and then when it hit the table here, it stopped again, and some of the energy was dissipated by moving around the lead shot, and scientists say that actually some of it was changed into heat.
Really?
Right. In other words, anytime you have sort of friction or an impact, some of the energy is absorbed in the form of heat. You and I are going to see if that's really true.
Maybe the scientists are wrong.
Well, maybe, yeah. We're going to do it with lead shot, so pour the lead shot into this tube.
Okay. All of it?
All of it, go ahead. Okay. Now, instead of dropping it like I did, I'd like you to turn the tube upside down so all the shot that's there is up here, but it's going to drop. Go ahead. Okay. Now, theoretically, each time it drops down,
It'll
it
get
should
heat-
get
get
a
hotter,
little warmer.
hot.
Okay.
Yeah.
So instead of putting that top on,
Put
here's
that
the
top.
thermometer, and you see I have a top here with the probe of the thermometer sticking out there. So put the top onto the tube.
Okay.
Okay. Now I'll do the work and you do the reading. Okay.
Okay.
What does it read?
24.3.
24.3.
24.4. 24.5.
Okay. Wait till it settles down. What is it now?
24.6.
Going up or still or stopping?
24.7 now.
Okay. Take my hand away. Maybe I'm warming it up.
Yeah. 24.8 now.
Okay. Ready?
Yeah.
Okay, here it goes.
24.9. 25. Still 25. 25.1. 25.1 still. 25.2. 25.2. 25.3. 25.3. 25.3 still.
Still 5.3?
25.4.
Okay.
25.5.
Okay, so we're going up, right? So you think the scientific theory is correct? That every
Yes.
time there's an impact like that, some of the energy is lost as heat? Good. I'm glad you agree. Thank you for helping to prove a scientific theory.
Now it's 24.6.
Okay, Brian, would you take a paper towel and put it on the glass plates?
Okay.
Put the fern on top like that. Okay, you know what to do? Okay, you've done this before, I think, right?
Yeah.
Okay. Now, do you know how to work a microwave?
Yes.
You push the button, right? Okay.
Yeah.
So turn it on for 1 minute.
Okay.
And put that little flask of water in there, too.
Yes.
So you have an idea what we were doing?
Yes, I think we're drying plants.
Yes. Obviously, from the way you knew what to do, that you've done it before.
Yes.
What did you do?
I didn't use a microwave. I just took some paper towels and 2 books and just put the plants between the paper towels and put 1 book on top and 1 book below.
Right. And how did it come out?
Well, it came out okay, but then after a couple days, it started crumbling, all the plants and things, all the plants.
What
and
kind of
leaves.
plants did you use?
I used a daisy, some leaves, and some plants. I didn't know what they were.
Okay. Now, the problem was probably not that you didn't dry them very well, because that's a fairly standard way of drying plants, putting them between 2 paper towels and then putting a weight on the top of it. But the problem is that you should have mounted them in some way. For example, here is baby's breath.
Yeah,
And because this is a very delicate sort of plant, you want to mount it on a picture frame, something like this, so that you protect it. And it'll last for years and years and years. That's a baby's breath, another one of my favorites. Queen Anne's lace. Especially these delicate ones you have to mount this way.
Yeah.
Microwave is done? Not quite, almost, okay. When it's done, I want you to go bring it over here, but be sure and bring the flask with you, because the flask was the water was very important in it, okay?
Okay.
Now, you see, a microwave dries food or cooks food by boiling the water away. So because there wasn't much water in the plant, I put some extra water in there, so in case it boiled away all the water in the plant, it wouldn't ruin the microwave. So you just put some water over off the side. Okay, you know what to do. All right, you're an old hand at this.
Take off the glass plate.
Off comes the first glass.
Okay. Now you take off the first one, first paper towel, which is full of moisture.
Okay, yeah, full of moisture. Okay, now put it over here on that picture frame.
There's also quite a mark.
Yeah,
in
you
the,
can almost see the pattern of
Yeah.
the leaves there. Okay, now put that on top.
nice yellow
Okay,
background.
put that over.
Okay.
Then
Cardboard.
temporarily, just help me put these little pieces of tape on it so that you can get an idea what your work of art looks like when you dry a plant in the microwave.
Hey, it looks good.
Yeah. Kelly, do you know what a pendulum is?
No.
Well, you've seen a grandfather clock. There's that thing that goes back and forth.
Oh, yes, that circle thing inside the door.
Right, yeah. That's a pendulum. This is also a pendulum. A pendulum really is a weight at the end of a string or a chain or a rod, and the weight makes it swing back and forth like that.
Yeah.
Okay? Now, I'm pretending this is a pendulum mounted on the earth, and you see I have north, south, east, and so forth. West is over here. Okay, I'm going to swing the pendulum, and then I'm going to turn the earth underneath it. You watch what happens.
Okay. It's moving. Well, it looks like it's moving.
What's
'cause
moving?
The earth is, but it looks like the pendulum is
Now,
because...
the pendulum is staying in the same plane, right?
Yeah.
And the earth is moving underneath it. Now watch. There's 6 hours. There's 12 hours coming up like that. Here comes 18 hours. And here comes
24 hours.
24 hours. Notice the Earth turned underneath the pendulum,
And it's still moving.
and they're still moving in the same plane. Now, this is called a Foucault pendulum after the scientist who devised it, and they very often have them in science museums. A great big long string or wire or something, and a big weight at the end, and as it goes back and forth, as the Earth turns underneath it, it knocks over little pegs.
Oh.
And if you stand there long enough, the whole Earth will turn underneath it, and it'll be right back where it started.
This voice print was made by a rather unusual voice. Listen. It was the song of a male white-crowned sparrow. Dr. Myron Baker of Colorado State University is studying how songbirds communicate. In one experiment, he places a female white-crowned sparrow into a test chamber. Watch what she does when she hears the recorded song of a male white-crowned sparrow. She flutters her feathers and trills, which are typical mating responses. She reacts as though a male is present. Dr. Baker has discovered that songs of the same species can vary according to the area in which the bird lives. Here's a home dialect, slowed down to 1/4 speed. Here's the song of a sparrow from another area. The female can tell the difference because she doesn't respond as much to it as she does to her home dialect. Dr. Baker's latest research has found that a female songbird selects her mate on the basis of not only how well he sings, but also, in some cases, how many different songs he can sing. There's more to a bird's song than meets the ear.
Okay, here, take the tongs, take a chunk of dry ice,
Okay.
see if you can put it in the top up there.
Okay.
Very good.
It has bubbles coming up now.
Right. You know what's in those bubbles? Have you ever played around with dry ice before?
No.
Well, when dry ice sublimates, or it doesn't melt, it changes directly to a gas. The little bubbles are full of carbon dioxide gas and water vapor. That's what
Okay.
makes them light colored. See how the sort of fog we're getting here?
Yeah.
Okay, go ahead, put some more in. Because in the water inside the tube, I have what is called a universal indicator. Have you ever played with a universal indicator?
We've worked with an indicator before, but not a universal.
An indicator, what did you do?
Well, we worked it like we had the litmus paper, and we put it by ammonia, and then it turned blue.
Turned blue, okay, it was red to start with.
Yes.
Now, so what did that tell you about the ammonia?
I forget what the word is called, but it's almost like alcohol.
Okay, an alkali.
Alkali.
Yes, that's a certain whole group of chemicals, right?
Yeah.
Well, this is an alkali at the moment, you can tell, because it is this blue color.
Yeah.
And as it changes to less alkali and more toward the acid side, it changes color. That's why it's called a universal indicator, because it'll tell you both acid and base or alkali. So here, put some more in, because as the carbon dioxide gas goes up through the tube, some of it dissolves in the water and makes the water slightly acid.
Okay.
Put some more in.
Okay.
Now keep an eye on the color, because it should change as it becomes less alkali and more acid.
It's no,
See any change yet?
not really.
Okay, put in another one.
Okay.
Chemists do this in little test tubes and beakers, but I thought it was more fun to do it in a great big tall tube like this.
It's changing color now a bit.
Is it getting, can you see it's slightly greenish as it goes up
Yeah.
here?
It-
Okay, now look at the color.
Yellow, almost.
Yeah, well, it's greenish.
Now it's
Now it's
yellow.
gradually moving there. Now it's going to get more and more toward the yellow side as it gradually moves over and becomes acid.
Yeah.
So it's kind of fun to have a bubbling column of universal indicator. Put another one in.
Okay. What are you putting inside the balloon?
Well, this is a common gas that's flammable, and you and I are going to combine it with the oxygen in the air by bringing a flame near it, okay?
Okay.
And what I'd like you to do is to notice sort of the characteristics of the flame. Now, there's some tape right there. So come on down here.
Okay.
See the rope I have stretched there between those two stakes?
Yeah.
Tape the balloon over here, way on that side over there. Okay, now tighten up the rope so that it doesn't get in the way of my torch, okay?
Okay.
Okay, so now I'm gonna light the blowtorch so we have a flame right over here. Okay? I wanna move the torch way back here too, and you'll see why. Now, at the other end here, you can now use the ropes and slowly bring the balloon over to the torch and watch what happens.
Whoa.
Okay, now I want to go turn off the torch.
Okay.
Meanwhile, you put the other balloon on that stopper. Okay. Now you noticed what kind of a flame that was?
Yeah, it was just a big flame.
Sort of the orangey sort of color, and not much of a loud pop. That's because when we combined the oxygen in the air with the balloon, the gas that was in the balloon, it wasn't a complete combustion. In fact, you probably didn't notice it, but there was probably a lot of soot that actually went out from it also. So I'm going to put only this much gas this time, and now add oxygen. So this means when the chemical reaction gets started, the oxygen is already there, and it can now be much more complete. Hear the noise?
Yep.
That's the oxygen going into the balloon. Okay, now, according to the chemical formula, there should be about 5 times as much oxygen as there is gas, so we sort of have to estimate that. That's probably good enough. Okay, now you know what to do.
Yep.
Got the tape ready. Okay. Here you are.
Okay.
Take this part off so it won't get stuck in the pulley. Okay? Okay, now I'll light the torch again.
Okay.
I shut it off awfully tight. There we go. Okay, now I want you to notice the difference in the kind of flame, okay?
Okay.
What do you suspect is going to happen?
It's probably going to be a bigger bang.
A bigger bang? Okay, let's see if you're right.
Whoa.
Notice no flame? It really just completely disappeared?
Yeah.
A real 4th of July chemical reaction.